Hello, in this video I would like to introduce you into programming with lists. Uh, Similarly to other languages, also in Haskell we need some sort of basic data structure that will hold some set, array and so on of data. Uh, in languages like C++, in these imperative languages, usually the most basic data structure that you can use are arrays. In functional languages, this function is provided by lists. Uh, I will try to introduce you how to work with list in Haskell, what the list in Haskell looks like, how do you recognize that you are using list, and so on. So first of all, lists are homogeneous data structures. So in one list, you can have, for example, some numbers, some characters, some cars, but you cannot combine numbers with characters or with other data types. Uh, Later we'll be talking about user-defined data structures. So here I will show you some way how to define a list, but most of constructs that we will be using to handle lists, to define lists and so on are some sort of syntactic sugar. So there are some uh, special ways how to treat the list in a way that is, let's say, a special for list and that cannot be used for other data types or requires a more work. So if we are talking about lists, how to imagine this list, sometimes it's also called this structure is also called a linked list. So the basic idea is that if I'm giving you a list, I'm giving you the first element, and the element in the list contains some data and some sort of reference to the next element. So here you can see some list containing 1, 2, and 3. At the end, there is some special character or special mark that we have reached the end of the list, and there is no other element in the list. So the list is pointing to nothing. Usually it's some sort of null, some pointer to nothing. If we are comparing a list with an array, so some operations, some basic operations that are manipulating this list have, let's say, a different time complexity. The value of this operation is different. So the basic idea is, if we are talking about list, so it's easy to access the first element, and it is easy to handle the head of the list. If we are talking about array, the easy operation is to get the end element from the list. For the array. For the array, we are able to compute usually the address, some sort of point arithmetics. We are able to compute the address of the end element and directly access it. If we want to perform the same operation with list, we get the head of the list and we need to go through all elements in the list to reach the desired element, and then we can get the value from this element. So this is maybe the biggest difference. So at one point, it's easy, for example, to add new element at the beginning, contrary to array, where we need to, in fact, create a new array. If we want to add some element, create a new element, create a new array, copy all elements from the old array into the new one, and then add this new element. In list, we can work with the head with minimum other requirements. So it's very easy to add new elements at the head of the list, get first element, and so on. But it's much harder to get somewhere inside into the list and add, for example, a new element at the end. Then we need to perform nearly the same operation as for array. So in fact, we need to create a new array, and we need to create a new list that will hold more data, that will have some new element inside. So how to define a list? At the top of this slide, you can see some definition. It's, let's say, closer to the real data definition in Haskell. So if we are defining a new data, we are defining some type name. Here it's a list, and then some data constructors. So some ways how to define this data. We will talk about it later. So you can see that a list of some type A, again, we are using this polymorphic, this data type is a polymorphic data type. So it can be a list of numbers, list of cars, list of some shapes, and so on. And then there are two ways how to create a list. It can be this nil, some sort of special mark at the end. So we know that there are no more elements. It can be, from the other perspective, it can be an empty list. And then some constructor that adds a new element to existing list. So we have an existing list. In fact, it's the second list referred in this type constructor cons. And then there is some value, in this case denotated by this A. So if we have a list of numbers, then here we put some number. So this is, let's say, some definition of a list, how it really look like if it's just a user-defined data type. As I said before, there are some special construct, some sort of syntactic sugar that adds or improves a way how we can manipulate this list, because it's some sort of basic data structure and we want to have some easy way how to work with lists. So the first such construction is the type definition itself. So instead of writing list of integer, list of something, list A, we are just using these brackets and write the type in these brackets. By this, we are telling the system that we want to use a list of this type A. Second such construct is this column. So instead of this data constructor that constructs a new element in the list, we are using this column. Later we will be using this operator frequently in our exercises. So you can see that its type is some element that we want to add to a list, the remaining list, and it will produce a new list where there will be a new element. It's the same like the constructor from the previous definition. And finally, instead of some sort of nil, we will be using just empty brackets. So it will be a special, let's say, symbol for empty list. In the examples, you can see two possibilities how to define a new list. So first of all, you can use this column operator. If you write 1, column 2, column 3, and this empty brackets, then in fact you are defining a new list containing 1, 2, and 3. Second option in Haskell, how to write a list. If you want to write a list containing center number of elements, you can use these brackets and put some elements separated by this comma. In this way, you can define also a constant list with the constant number of elements. So this is some basics how you can define a list, and some basic, let's say, language constructs that you can use to define a list and work with a list. So now we know about a list like a data type, and we need to speak about how to handle lists, how to work with them. In the previous videos, we have talked about different ways how to define a function. So the primary technique that we have used to define a function in Haskell was the pattern matching. So it was some ability to define a function like a set of rules and then there can be a different right side, different expression that will be chosen on based on this pattern. So if we are able to match these patterns with the input, then the corresponding right part will be chosen. So in this case, I will show you some special patterns that you can use for lists. So first of all these rules that were used before still applies. So let's say that we will be writing a function length. Function length is already there, so I will use a special version length with this apostrophe. So let's say that we are writing function length that computes the length of the list. What are our options how to write this function? So we have function length with apostrophe. So first of all these rules that or all these patterns that we have already talked about can still be applied for lists. So our two most basic patterns were a constant. So let's say that a length of a list containing just one, we can say, okay, so it's one. Similarly, let's say that we want to write a length of a list containing numbers 1, 2, 3. So the length of this list is 3. So here you can see this can be a potential solution for the function length. Of course, such trivial cases, there are plenty of such trivial cases, and function written like that won't be really working. So how about some better patterns? So we can use also second option for the pattern were some variables. So again, we can use some variables. So let's say that we have some variable x. It can be also used for a list, but right now we really don't know what the length of the list is. So we will talk about it a little bit more later. How about these patterns? Can they be replaced with some variables? And the answer is yes. So here, for example, I can use this pattern. In fact, this x can be any list, but in this case, I have written a pattern that corresponds to a list containing exactly one element. In the second option, I can use again variables for these values. So I have a pattern containing exactly 3 elements. So these are some ideas, these are some examples how to write some patterns that will cover some list of constant lengths. What remains is, what if we don't know how long is our list and still we want to compute its length? In this case, we will be using this colon operator. So we can use this operator inside in our pattern. In fact, we are using this constructor that was on the previous slide. So in this case, we are in fact referring to this constructor that is creating the element of the list. So we want to match this. So if we use a pattern x.xs, here this x and xs are just frequently used names. It's like the x, the element of the of the list, and xs is something like a lot of elements x. Names like a, b, c, c, d, e will be can be also used. So what about this pattern? Later, the system will try to match the given parameters with this list. And based on these ideas that I told you before, if I gave you a list, for example, let's say 1, 2, and 3, so in fact, there was just one way how this list was created. In fact, what we did is we have add the first element into some existing list. So at the end, in fact, something like this was done. So we have put new element, we have created new head for a list, and it contains this last or the first value and the remaining list. So if we have this pattern, so the only option for the list or only option for the system is to map the first element of the list as x and the remaining elements as the list xs. From this perspective, it's also called some pattern for unempty list, because the smallest possible option in this case is if we have a list containing exactly one character. So let's say that we have a list containing just one, and then some sort of remaining list. So let's say this nil, this empty list. So this is the in fact it's a list containing just one element. So this is the smallest option that can be matched with this x column xs pattern. So in this case, this x is 1 and this xs is this empty list. So using this pattern, we can match any non-empty list. So here we can use it also for list which lengths we don't know. So we can handle in this way we can handle any list, we can work with the list and so on. So what's the basic idea if we are talking about this precise function length? We want to compute a length of any list. So what we will do, and I will write the solution, and then I will try to explain the solution. So we have something like length xs. These rules are not necessary. So we say that the length of the empty list is 0, something like that. So what's the meaning, or what's the solution itself? So what's the basic idea? What's the algorithm that we'll be using for computing the length of the list? So in fact, we don't really care about the elements in the list, but we just want to add one for each of these elements. So you can see here some sort of recursion that goes through the elements in the list, and for each such element it takes the element, in our case it's named as x, and counts 1 for each such element. So here in this slide you can see how this function will be rewritten if I start it for the list 1, 2, 3. So first it will be rewritten as 1 plus length of the remaining list. In our case the xs will be list containing 2 and 3, and later it will be rewritten as 1 plus length of the list 3, and so on, until of course every recurrent algorithm needs to end somewhere at some point, if we are not working with some unending structures. So in this case, we for sure we know the length of the list containing no characters. So if we use this, so the length of this empty list is 0. So at the end it will be this 0, and then this expression can be evaluated, and for our example it will be 3. So we have a way using this pattern x column xs. We have a way how to handle these lists of any length, and we can write some functions that goes through this list, that work with this list, and so on. We can slightly improve this function. So here we can use this underscore instead of x. This underscore is sometimes referred as discard. So in places where we know that there should be some sort of variable, but we are not really working with this variable, and we can discard the value. We can use this discard character, discard operator sometimes it's called, and you can see that we haven't really changed the meaning of the function. Just the variable x was previously not used on the right side. So the basic idea is that such variable, we don't even need to name such variable. So we are using this underscope, this discard in this case. Finally, let's talk about the type of this function. So it was already mentioned before, but Haskell supports some polymorphism. You can define some polymorphic data types, and also these functions that are working, the function can work with different types. So we can have polymorphic functions. How do you recognize them? They use this type variable. So if you think about this function length, we don't even use, as I mentioned before, we don't even use the element. It's not we don't even need to name the variable that represents the element in the list, the value really stored in the list, but we just count one for each such element. So in fact, such a function can be used for any list. It can be used for a list of numbers, list of characters, list of lists, and so on. So what is the type of this function? And let's say that if you want to define the type of this function length, we can write it like this. Yeah. So right now it's a function that takes a list. We know that it's a list because it's some type variable in this brackets. So it defines that it is a list, but the type is a, so it's a type variable, and later we can put there anything. So there are no constraints here for this type a, and the result is integer. So the result will be the real length of the, or the result will be an integer. It will be the length of the list. So this is some example of polymorphic function. If we want to try it, we can call our function length for a list of numbers, for example, like that, or we can use some characters like that. So it's working, and in the first case, if we are asking what's the type of the list, so it's a list of integer. In the second case, it's a list of characters. We can try it. So in this case, it's a list of some numbers. If I put there that any of these numbers is int, so it's a list of integers. So based on the definition, we know that it's a list, and this function is working on any list, so it's a polymorphic function, and we know that because it's used this type variable in its definition. One remark considering this polymorphic types and polymorphic functions, sometimes we need to somehow restrict the types that we are working with. As an example, let's say that we want to write a function is element, which takes an element and a list, and the output will be true. So it will be some sort of boolean. It will be true if the element is contained in this list, and if it's not, then it will be false. So the basic idea can be okay. So I will say we have some type A, it will be the type of the element. We know that these lists are homogeneous data structures, so it needs to be the same type. So we have a list of the same type. And finally, the answer will be that there will be some sort of bool like a result. So if we are writing this function as element, again, we can use this recursive approach. So if the end will be if we have an empty list, so there the answer is false, there is no such element. So let's say that we have anything, then empty list, and finally the answer will be false. Second option is that we have an unempty list. So we have some element, some unempty list. We can use the pattern as before. And now we have, in fact, two options. In previous video, I showed you, for example, this guard expressions. So it's another construct that I can use when creating some programs in Haskell. So the definition of the function is split into different options, and each of these options have some condition, and if it's evaluated to true, then the corresponding part is chosen. So in my case, I have two options. I can compare the value with this epsilon, and if it's true, then I know that I have found my element, so the result is true. And if it's not, then I need to use the recursion and call the function its element again for the element x and for the remaining part of the list. So this function is it seems to be okay, but still there is an error, and the error is related to the operation equal. Yeah, it's not easy or it's not clear that I'm able to compare two types. For example, if I have some, I don't know, irregular numbers, when these numbers are really the same, how can I compare it? So if I have my special type, so not always there is a way how to compare two values of this type. And if I want to do that, I need to provide a way how this operation will be solved. In Haskell, these conditions, these operations are solved by type classes. On the slide, you can see a definition of the type class equa. It's a special type class that, or a type is in this type class if two values of the same type can be compared between each other, and if they are equal. And in this case, what I need to tell to the system, to the compiler, is that this function is element is not for any type, but only for types that belongs to this type class, only for types for which I have defined this operation equal. Yeah, so this can be done by some restrictions that are placed on this type variable. So in fact, in this type definition, before the real type definition, I can have this double arrow, and before that I can have some conditions. So in my case, like this, I'm able to say that not every type is suitable for my function is element, but only the type that belongs to this equa class. So what is this type class? You can see it on the slide. We'll talk about it later in more details. So this type class, in fact, defines some operators or some functions that needs to be provided when the type becomes a member of this type class. Here you can see that there is a keyword class, but it's not related to some data structures like in object-oriented languages like Java or C#. But here it defines a type class. Moreover, you can see that this type class is defined for two for two, in fact, operators. Later we will be talking about operators in probably next video. So I can show you if you want to define a new operator, the definition is nearly the same as for a function. And we already know that if we if we put the operator into this parentheses, then it behaves like a function. So probably it's not that strange to see that here we are defining these two operators similarly to functions. So informally, if we have a type class that we have defined some operators or some functions that needs to be provided with this type class, then if we want to if we are creating a new type and we want to put this new type into this type class, then our task is to provide these operations. For this class equa, you can see that there are two operations, something like equal and not equal. And of course, if we have the operation equal that we already know how to solve not equal, so here the Haskell supports some sort of combinations of these operations. So we are able to define one operator using the other one or the other members of the class and so on. So later, if we are defining this operation for our new type, then we don't need to provide all these operations, but just some necessary operations if the other ones are we are able to compute, or are there is we have defined a way how the others can be solved using this small subset. So in our case, for example, we have provided how to solve this not equal operator if we have equal operators. So it's enough to provide equal operator because we have a standard way how to solve not equal if we have the equal operator. So this is some basic idea about these type classes, and we'll write some functions that work with this type classes, or that requires them. So it's just to know what's the meaning of this double arrow and about this part that can be before the definition of the type. Finally, I want to make a remark about tuples. So second option to lists, in fact, are some sort of tuples. If you want to, for example, return 5 values from some function, then we can use some tuples or 2 values. So it will be pairs, triples, and so on. So tuple in Haskell is in these parentheses. In contrary to lists, tuples can have values of different types. So here you can see a triple which contains a number, a list, and some string. So if we have a tuples, so how to work with these tuples? In fact, anywhere, again, if we use, for example, a pattern matching, and if we want to work, if we want to parse these tuples, then we can use then we can use this pattern containing a tuple. On this slide, you can see, for example, a function addDem that takes a tuple and returns the sum of these two elements in this pair. Also, the system generates some special functions that are able to take first, second, third, and so on element from these tuples. So if we have, for example, pairs, then there are function first and second. First returns the first element of pairs of the pair, and the second returns the second element of the pair. So second option that we'll be using in laboratories are these tuples. You can recognize a tuple if some functions takes a parameter and if it's a tuple, for example, a pair in this example, then you can see that there are these parentheses also in the definition. So elements in tuples are divided by comma. So here you can see some examples, something like two integers in one pair.